and welcome everyone to one more lecture of probability and statistics. Today we will learn about Poisson distribution and moment generating function. First of all, Poisson distribution. Poisson distribution is a limiting case of binomial distribution under some conditions. First condition is n, that is number of trials tends to infinity. That means number of trials are indefinitely large. Second, p, probability of success of each trial is indefinitely small. That means p tends to 0. And third, that is our mean value np equals to lambda, and this is finite. Lambda has a finite value. Poisson distribution is a discrete probability distribution and it is used to show number of events that are likely to occur in a given time period. Now, probability function for Poisson distribution. P lambda p x semicolon lambda. Lambda is parameter of Poisson distribution and x is random variable of Poisson distribution, and it only takes non-negative values. So it only takes 0, 1, 2, so on, whole numbers only. And this equals to e raised to power minus lambda, lambda raised to power x by x factorial. This is the value for probability function of Poisson distribution. Mean of Poisson distribution equals to variance of Poisson distribution, and that equals to np, and that equals to lambda. Lambda equals to np equals to mean equals to variance for Poisson distribution. Now we will solve question on Poisson distribution. Our question is, a random variable x has Poisson distribution with parameter lambda such that p of x equals to 1 is 0.2 times p of x equals to 2. We have to find p of x equal to 0. Now, our formula for Poisson distribution is p x semicolon lambda equals to e raised to power minus lambda, lambda raised to power x by x factorial, where x only takes non-negative values and lambda is mean value. Now, our lambda value is unknown. P of x equal to 1 will be e raised to power minus lambda, lambda power 1 by 1 factorial, e raised to power minus lambda times lambda. P x equal to 2 is e raised to power minus lambda, lambda raised to power 2 by 2 factorial. This will be e minus lambda times lambda square by 2. Now we have a relation between p of x equal to 1 and p of x equal to 2. That's why p of x equal to 1 is 0.2 times p of x equal to 2. Now p of x equal to 1 by p of x equal to 2 is 0.2, and we can write 0.2 as 2 by 10. Now we will just put values of p of x equal to 1 and p of x equal to 2 here. So this will be E minus lambda times lambda by E minus lambda times lambda square by 2 equals to 2 by 10. E minus lambda would cancel out. Lambda, lambda. So this will be 2 by lambda equals to 2 by 10. That means lambda equals to 10. Now we have to find P of x equal to 0. P of x equal to 0 will be e raised to power minus lambda. Lambda value is 10. E raised to power minus 10. Lambda 10 raised to power x, that is 0 by 0 factorial. 0 factorial is 1 and 10 power 0 is 1. So this will be e raised to power minus 10. This is our answer. Moving on to our next question. We have a question. A car hired 2 cars which hires day by day. Number of demands for a car on each day is distributed as Poisson variant. That means number of demands of car follows Poisson distribution with mean lambda equals to 1.5. We have to calculate proportion of day on which first neither car is used. Neither car is used means there are no demand for cars. That means if x denotes number of demands of car, then x equal to 0, as it follows a Poisson distribution. Probability distribution for Poisson is px semicolon lambda is e raised to power minus lambda raised to power x by x factorial. Putting value of x and value of lambda, p of x equals to 0 will be e raised to power minus 1.5 lambda 1.5 raised to power x 0 by 0 factorial. 1.5 raised to power 0 will be equal to 1 and 0 factorial also equals to 1. So this will be e raised to power minus 1.5. You can solve this value further also. Our second part is some demand is refused. When we will refuse the demands? When demand is greater than number of available cars. So available cars are 2. So probability of x greater than 2 is the condition when we will refuse the demands. So this will be equal to 1 minus probability of x equal to 0 minus probability of x equals to 1 minus probability of x equals to 2. Putting the values 1 minus p of x equal to 0, we have already calculated this value. This will be e raised to power minus 1.5. P of x equal to 1, e raised to power minus 1.5 times 1.5 raised to power x, that is 1 by 1 factorial, that is 1, minus p of x equals to 2, e raised to power minus lambda raised to power x by x factorial. You can solve this value further also, or you can leave it in 1 minus e point minus 1.5 taking common, 1 minus 1.5, 1 plus 1.5 plus 1.5 square by 2. This is our solution. Our next subtopic is moment generating function. Moment generating function for a random variable x. moment generating function. Moment generating function for a random variable x with probability function f of x is defined as mxt equals to expectation of e raised to power dx, and for discrete this equals to summation e tx times f of x, and for continuous case this equals to integrate minus infinity to infinity e raised to power dx f of x times dx. Moment generating function about a line x equal to a can be defined as m x minus a of t, and this will be e of e t times x minus a. We have two properties for mxt. First is mcx of t equals to mxct, where c is a constant multiplied to x. Second is, if we find moment generating function for a sum of random variables such as x1, x2, so on xn of t, so this will be equal to mx1t. If they are in sum here, they will be in multiply on the right side, mx2t, so on mxnt. Now we will solve a question on moment generating function, as it is a very important topic in our syllabus. We have to find moment generating function for a discrete random variable, as you can see from this probability distribution. With probability distribution 1 by 3 for value x equal to 1 and 2 by 3 for x equals to 2. As we know, MGF is denoted by mxt, and this equals to expectation of e raised to power dx, and this equals to, for discrete, summation e raised to power dx times f of x. So this will be e raised to power dx into f of x for summation of values of x. Now value of x, this will be value, if we put first value of x equal to 1, then this will be e raised to power t times f of x. F of x is 1 by 3 plus e raised to power t into x. X is 2, e raised to power 2t into f of x 2 by 3. We can also write this as e t plus 2 times e raised to power 2t by 3. This is our MGF for random variable x. This is all. We will meet in our next lecture. Thank you.